CovertCast, which is, as we just said, a system designed to use live streaming services like YouTube to evade internet censorships. My co-authors are Amir and Vitaly. So normal censorship-resistant setup involves a user inside of some sort of censored region who wants to access some kind of blocked or forbidden content. We assume that there's a censor or other adversary monitoring this content, or monitoring all the incoming and outgoing connections and doing some sort of possible filtering. The user ideally wants their traffic not to be recognized as accessing the forbidden content. And there's a number of services and systems out there that allow you to do this or attempt to do this, including Tor. However, oftentimes on closer examination, it's easy to detect what these censorship-resistant services are. So when thinking about this problem, we asked ourselves what other systems existed that were allowed to cross the boundaries of these censored regions. And there are a fair number of them. Some of them include encryption, and so we decided why not use those and hide our content inside of that. Specifically, we looked at live streaming video services, which are things like YouTube and Twitch TV, that have high bandwidth encrypted communication, allow us to scale effortlessly and are free. And so we designed CovertCast to broadcast websites through these live video streaming services. So as I said, these services are things like YouTube and Twitch that allow you to upload a live video and people can watch it in real time. This is different from the normal YouTube videos where you'd upload it and someone would come around a week later and watch the video. When you watch the video on these services, you're watching it in real time or very close to real time. So YouTube allows you to live stream anything or almost any sort of content. For example, in 2016, Coachella concert was viewed by over 21 million people. This was a live stream of the concert. YouTube also supports password-protected and invite-only live streams. Twitch TV is the other really popular, really well-known live streaming service. It focuses mostly on video games. It has more than 9.8 million monthly viewers, but does not support private streams. So we designed our system CovertCast to use YouTube, but it's almost completely system as agnostic, so it can be easily modified to use other services like Twitch or the dozens or hundreds of other live streaming services that cater to general audiences or niche-specific groups. So how does a live streaming service work? Well, a broadcaster records a video of themselves in real time and uploads it using a protocol like RTMP, or the encrypted version of RTMP, RTMP-S, to these live streaming services. And then any number of clients can connect to this service and watch the video as it happens. What we'd like to do is replace the dancing frog in the previous slide with some sort of censored or forbidden website, in this example, BBC News. However, just replacing the dancing frog doesn't quite work because it's a video of the website. So it's almost static, the user can't interact with it, and this isn't any good. So instead, what CovertCast does is it downloads content from these websites, the HTML, JavaScript, images, etc. It modulates this content into images and uses these images as frames in the live streaming video that it uploads to YouTube. Then any client can watch YouTube, demodulate these images back into the original content, and interact with the website as normal. So this is an example of one of the images that we use for our video frames. It's 720 by 1280 pixels. It's composed of these thousands of colored squares. Each of these squares is 8 by 8 pixels and encodes 6 bits. We put 2 bits in each of the color channels. So we investigated using more than 6 bits here, but when you upload an image to YouTube or one of these other services, there's some slight degradation in quality. We think due to format changes or compression on the back end. So what you're actually uploading to YouTube isn't quite what you're seeing on the other side, which is why we're encoding in these color channels, but why we're sort of limited with how much we can encode or put inside of them. Now, given 720 by 1280 images and 8 by 8 pixel blocks, we get about 14,000 colored blocks per image. And with 6 bits per block, that's around 86,000 bits per image. But you've probably noticed the asterisk here. To help prevent these live streaming services from cropping the outermost pixels, which some of them do, some of these services do, we include an 8-pixel black border around the edge of these images. So we take the outside blocks and we just leave them black and don't use them to encode any data. This gets us down to a little under 85,000 bits per image. Now, we also include the possibility to use error-correcting codes in CovertCast. We found we didn't need them for YouTube, but they were helpful with some other services that we briefly investigated. So CovertCast uses 720p videos. We're able to do that because of the large size of the images. However, we're only able to send 2 images per second with YouTube. So we have to send 1 image for half a second and then a second image for another half a second. The reason for this is YouTube does not support rapidly changing frames where every color is switching between another color in between, 10 times a second or so. If you try to use more than 2 images per second, you start seeing image artifacts in the graphics, or frames or images get dropped, and that makes CovertCast unusable in this. However, still sending 2 images per second gets us about 169,000 bits per second. Now, CovertCast is designed to be used by clients inside of censored regions. So once more, their content is being monitored by some censor, everything coming in and out. Conveniently, YouTube encrypts all video communication between the servers and the clients. On top of this encryption, with this encryption, it's hard for an adversary to use the current deep packet inspection or other sort of protocol fingerprinting to figure out what content or if CovertCast is being used as opposed to viewing a normal video with YouTube. We also investigated the metadata involved with these, the video packets. We looked at the packet sizes and timing, and we found that we were unable to distinguish CovertCast videos from other YouTube videos to any major degree. Now, I need to mention right here a small errata from the paper. In the paper, we incorrectly identify that the server, the CovertCast server, is uploading encrypted images or encrypted video to YouTube. There is an encrypted version of the protocol that YouTube uses, but YouTube does not support it. Now, you may have noticed that CovertCast is one way. The information only flows in one direction, and there's a reason for that. Live streaming services have an inherent latency. This is just part of their system we found of all the services we've investigated. So when you upload a video, if you're uploading a video of yourself and you wave and say hello, it's going to be around 30 seconds before anybody watching the video sees you wave and hears you say hello. So with CovertCast, that means if a client were to send some sort of GET request to the CovertCast server, and the server carries out that request, gets the response, modulates the response into the images and uploads them to YouTube, it's going to be around 30 seconds before the client actually gets the response to the initial request it sent. This is especially unreasonable given the fact that most websites have hundreds of pieces of individual content, each of which require their own requests. So what CovertCast does is every server is connected or associated with one or small number of websites. It has a web crawler that crawls through these websites, downloading the content, and then continually modulates the content into images and uploads that content to YouTube. A client continually monitors the video connection, demodulates the content, or demodulates the images into content, caches it locally, and then can respond locally to any request from the browser on the client. We've implemented these web crawlers for 5 news sites with CovertCast. Each of them take less than 30 lines of code. They're very easy to make. The 5 sites we have are 5 news sites: the USA Today, New York Times, The Guardian, Wall Street Journal, and BBC News. Currently, our functionality for the web crawlers are to send the front page of the news website and then some set number of linked articles from the front page, then the front page again, and then another set of linked articles. However, this functionality is also extremely easy to change. So as I've mentioned, CovertCast is completely one-directional. However, as an added benefit of that, we're able to scale very easily. And in fact, every additional client is no extra burden on the CovertCast server. This is due to the fact that we're using YouTube or these other streaming services, which are meant to be one-to-many broadcast. So, so YouTube handles every single individual connection from clients to YouTube, and the server, regardless of the number of clients, just has one video stream from itself to YouTube. We've implemented CovertCast primarily with Python 3. We use C++ for our video screen scraping. The server and client both use HTTP 1.1 proxies. HTTP 2 proxies would have simplified the implementation somewhat, but at the time, both Chrome and Firefox had bugs related to HTTP 2 proxies. We used FFmpeg for our video streaming, and our web crawling was done with the Ghost.py headless browser. To evaluate CovertCast, we loaded the front page in 3 news stories from all of our websites, and we had an average of 5 runs, or we took 5 runs and averaged the amount of time it took. To reduce the amount of content being sent, we requested the mobile version of these sites. We used a mobile user agent and an ad blocker on the server. As you can see, 4 out of the 5 news sites loaded in under 2 minutes, so it's about 30 seconds per page. The relatively large size of the Wall Street Journal is due to the fact that it did not have a mobile version of its site at the time and sends very high resolution images. So there's a lot more data that has to be modulated into images and sent. Now, we also looked at CovertCast, its use under poor connections. We looked at 10% packet drop, 800 kilobits per second low bandwidth, and we also examined high latency. However, high latency had very little effect on video load time. The packet drop and low bandwidth are really pushing what you can do with YouTube 720p videos. Much higher than 10% packet drop, you can't view the videos at all. And the low bandwidth is less than half of what YouTube recommends for these 720p videos. In both instances, the amount of time it takes to load a video increases. This is both loading the video, and then while watching the video, it stutters. You see some frames for a longer time and then some frames for a shorter amount of time. In both cases, there were also a small amount of images dropped. This is less than 1% of the total amount of images that were sent. So there's some issues with CovertCast. As I said, it doesn't work with AJAX or client interaction. There's no way to send information from the client to the server. Looking at any HTTPS websites requires some sort of man in the middle or other possible security concerns. However, as it's mostly passive browsing, this probably isn't too big of an issue. And then finally, it fails with some sites that use dynamic image loading. So for example, the BBC News, when you first load an article on BBC News, you get a very low resolution image. And then after the website is fully loaded, it requests a higher resolution image. CovertCast doesn't have these higher resolution images cached, and so responds with a 404, and the BBC News website replaces the low resolution image with these blank images on the right. Okay, so that's CovertCast, a censorship-resistant system with a few rough edges. It relies on live streaming services, which are free, high bandwidth, scalable, and encrypted ways to tunnel web communication, but they have a couple quirks. For example, the amount of images you can send per second, or the latency involved with them. And if you get nothing else from this talk, I hope you get that these are some really interesting services, and I challenge you all to try to go out and find other clever ways to use them, either expanding on what we've tried to do here, making it better, or finding other services or other uses for these services. Thank you.